very happy that I'm here, but thank Mr. Pahlevan for invitation and his colleagues, Adi for typing the brief glossary and Ahmed for printing them, and also Mrs. Ahsan that really, she was helping me for 24 hours. She has printed more than 2,000 pages and printing them and searching. Today I'm going to talk about time dilation. But before we go to time dilation, really it is important to know time dilation is exactly a radical consequences of special relativity. Then we have to go first of all to know what is the postulates of the special relativity. This is the Einstein Legacy. I didn't bring the simultaneous thing that we are going to get about 5-6 slides next. Time dilation and length contraction. Okay. The first question is, how fast are you moving right now on your chair? 0 meter per second relative to your chair, Delft, as you say, not to you, yeah? Delft. 400 meters per second relative to Earth, center is the rotation of the Earth around itself. 30,000 meters per second relative to the Sun, the orbitary movement of Earth around Sun. 220,000 meters per second relative to the galaxy center, and 370,000 meters per second relative to CMB, cosmic wallpapers. And I think you know all the others except the last one. CMB is cosmic microwave background, and we'll tell you once upon a time about the time of Big Bang. What is exactly cosmic microwave background? This is a kind of radiation. This fossil radiation, the furthest that any telescope can see, was released soon after the Big Bang. There is a nice story about that. I will tell you a little short story about that. It was about 1965 that two people, one of them Arno Pesario and also the other, they were not exactly scientists, they were two normal technicians. They were checking all the kind of, I didn't tell you the other one, Robert Wilson and Arno Pesario. They were checking all the radio frequencies from the galaxies. And suddenly they noticed that, it would be some kind of wrong thing about their instruments, or there was a pigeon nest around them and they cleaned that, and again they saw it is exactly the same radio frequencies from all over the galaxies to their instrument. They didn't know what is that exactly about. They were in America, in Pennsylvania, and also in Princeton. Two other people, they really, before them, anticipated that CMB radiation. And also there is one important thing that most of the time they say, you know George Gamow, I think. They predicted about a year, 2 years before that, 1964. And also Russian scientists, they somehow claimed that they noticed this radiation about 2 years before the American. But however, this is now registered with the name of these two people that I told you. Then the cosmic microwave background is the cool remnant of the first light that could ever travel freely throughout the universe. The time that universe was so hot, about 300,000 years, but sometimes they say 400,000 years, as NASA said. I will show you the slide. But that 300 years, the first 300 years of after the Big Bang, there was no opportunity for life to escape from that mess. But after that, we have this radiation. This is from NASA that they claim that it is 400,000 years. After that, the light can go and escape from that mess or quantum fluctuations. In comparison to 400 million years, it is nothing. But anyway, most of the scientists, they say this is a good evidence for Big Bang. You know, there is a model, standard model, that most of the time they say, no, the M theory or the string theories, all of them are on the table. But one of the most important one that most of the scientists nowadays, they believe is the Big Bang. They consider their discoveries as solid evidence for the Big Bang theory. This theory predicted that the shock wave of that primeval explosion would be still detectable as a subtle wallpaper coming from everywhere behind all galaxies, quasars and galaxy clusters. Today, the Big Bang model is still the only model that is able to convincingly explain the existence of the CMB. Okay. However, we go further about the speed of light, but here's something that I really hope you focus on it. The above picture is very ordinary in all places that you are passing by. For example, in Delft, in a playground, in a football game, in a baseball game, you can see that. You can name it Sally and Ali. Ali is hitting the ball, and the ball velocity is 30 meters per second. Sally is running, and this velocity for Sally is 10 meters per second. If you're going to suppose what is exact sum of the velocity that they are going to hit the ball by the hand of the Sally, you should plus them. 30 meters plus 10 meters, it is 40 meters. But now, go to the lower. That picture shows you the speed of light problem. There's an astronaut over here, and he has got a flash in his hand. And as you know, somehow, not exactly this, because it's not true, but we say now, for now it is good. We say 300,000 kilometers per hour or 300 million meters per second. This is the speed of light. At the same time, Sally, again now, is in a spacecraft, a spaceship over there, and she's going forward to the light. And the speed, the velocity for the girl is 100 million meters per second. If you want to go to Newtonian transformation or any kind of even Galilean transformation, you should plus together. It could be 400 million meters per second, but it's not true, it's really wrong. Correct Einstein description is here, as seen by astronaut in a spaceship. Light approaching her exactly the speed of light. This is the problem. And why this is the problem? We'll see that in next slide. It is better to go back to 300 years ago, 17th century. That time, absolute space. According to the most distinguished philosophers and scientists, time and space were absolute concepts. And even Kant said, space and time are properties of thought. In other words, they are a priori. You have it, that word in your glossary, but just you can see a priori knowledge as the knowledge that always it was there. The thing that they were in your thought, or always they were like the absolute time, absolute space. And the other example is mathematics. It's a knowledge that always it was there. The other explanation for a priori could be when you are not going to experimental or any kind of empirical evidence for getting a knowledge, it is a priori. And it is contrast to a posteriori. Then we have two kinds of knowledge. A posteriori, that always it is on the basis of the experimental and all the empirical evidences. and a prior knowledge. In that time, till 110 years ago, most of the distinguished philosophers and scientists really, they believe that time is absolute, space is absolute. Newton held also that space and time have an absolute reality in the sense of being quantifiable objects. Newton in Philosophia Principia of, in fact, Philosophia Naturalis Principia Mathematica. It's Latin, but English is Mathematical Principles of Natural Philosophy in the 17th century. Included his famous 3 laws of motion. Just we need the first one and the fourth. The first, that you know it, an object in motion will remain in motion unless acted upon by a net force. And the fourth one is the force of gravity is proportional to the product, the 2 masses, and inversely proportional to the square of the distance between the point masses. Why do we need Einstein? It is now known that Newton's universal gravitation doesn't fully describe the effects of gravity. And here I said that Einstein will arrive, but how? Einstein arrived, but not alone. This is very important for me, that most of the people that they are thinking about Einstein, they think Einstein really discovered everything from the vacuum. The vacuum for Einstein is just for the constant speed of light, but he was not thinking in vacuum. He was not alone. James Clerk Maxwell, that we'll see who is Maxwell exactly in this presentation. Hendrik Lorentz, Henri Poincaré, Max Planck, and Hermann Minkowski. Minkowski was a teacher of Einstein, the last one, and also we'll tell you a little bit about Minkowski. As you know, Einstein wrote all the formulation in algebra, but Minkowski wrote the special relativity and also space-time by geometry. For the first or second years, really, Einstein didn't believe that it is the kind of scientific geometry or something. He said this is a kind of trick, and he didn't believe Minkowski. But Minkowski in 1907, he died, but after that, Einstein was regret about that belief, because Einstein accepted that. I will show you. Max Planck really has no big role in special relativity. Max Planck has another role in the life of Einstein, and it was about the photoelectric effect that most of the people, I think, they suppose Einstein gets a Nobel Prize because of the relativity, but it's not true, it's wrong. Einstein really get the Nobel Prize in 1921 because of the 2 things. The first is theoretical physics, development of theoretical physics, and the second one was so important, it was photoelectric effects. And Einstein used a lot and owed a lot to Max Planck about that. This is because I brought Max Planck's name here. And Hendrik Lorentz, that you will see the Lorentz factor in this presentation, then I don't talk about that. Just about the Nobel Prize, I will tell you something as information. It's not bad. Einstein didn't go to Sweden in 1922 to get the prize. And also he gave all the money, it was about $1 million, to Mileva Marek. Mileva Marek was his first wife. But the funny thing is, in that time, she was not his wife. 2 years before they divorced. Okay, special relativity is easy to understand. It has 2 postulates, some predictions, and a little bit radical and revolutionary consequences. But please don't forget the constancy speed of light. Light speed, now I'm telling you the exact speed of light, is 299,792,458 meters per second. This is very difficult to imagine, and it is again the common sense. It is against the common sense. Why, I will tell you. Two postulates. It has two postulates. Then what are those two postulates? It was in 1905 that Einstein wrote that paper that you know. The laws of physics are the same in all inertial reference frames. The second one is light travels through empty space at c, independent of the speed of source or observer. These are the two postulates of special relativity. There's no absolute reference frame of time in space. The laws of physics are the same. This is not saying by Einstein. This is a postulate that's 250 years before Einstein. It was said by Galileo. Again, we're back to speed of light here, and Einstein started the special relativity here. Predictions of a special relativity. Simultaneous events to one observer need not be simultaneous to another. Time dilation. Our presentation is about this. And the last or the third one is length contraction. Then, now, time dilation that we are going to talk about today is one of the consequences or the radical prediction of the special relativity. We're back to Maxwell that I told you, we're back to it. The foundations of special relativity comes from Einstein's understanding of Maxwell equations. He realized that while they predicted the velocity of light, they don't say with respect to what this velocity should be measured. His equations, 4 equations, stated that the speed of waves is universal. Everywhere is the same. It means everyone measures the same speed regardless of any motion. It doesn't matter that Sally was going to that light by the 100 million meters per second. It is exactly, again, for Sally, the same speed. So either the speed of light is universal or Maxwell's equations are wrong. But Einstein proved that Maxwell is right. The radical consequences. Speed is easily equals to distance traveled over time elapsed. If the speed of light is a constant, then length and time must be variables. Again, if the speed of light is a constant, then one of these should be varied. Okay? These effects are known as length contraction and time dilation. Again, speed of light is 299,792,458. Always this is constant. What is the new definition of 1 meter? How we get this? In 1983 by the SI, this is the international standard for the quantities, that always they have a gathering and meeting and they show or they demonstrate what is 1 kilogram, what is 1 meter. And then they decided about the meter. The meter is the length of the path traveling by light. The meter is the length of the path traveling by light in vacuum during a time interval of the 1 over speed of light of a second. And what is second? The second is the duration of that number of periods of the radiation corresponding to the transition between the 2 hyperfine level of the ground state of the cesium-133 atom. We're back again to one of the predictions. Simultaneity. Time always moves forward. Time measured between things can vary. Then, lightning strikes point A and B at the same time, O or Mr. X, we'll see both at the same time and call them simultaneous. That was something that always Galileo said or Newton said, but this is not true on the basis of their special relativity. above. Light in center of car flashes hits front and back simultaneously. Yeah, this is true. Most of the time we see that. But if the observer is watching the car move, the car travels while the light is in motion. When the car is in motion, so the light hits the back of the car before the front. Vice versa to this. Time always moves forward, but it's not true here. The other example is this: simultaneity is relative. Whether two events are simultaneous depends on the frame of reference. Frame of reference. Always we have a frame of reference. Now we are here, we are sitting here. This is our frame of reference. I asked you the first question: how fast are you moving right now? To which kind of frame of reference? To Delft? 0 meter. But for the center of the Earth is 400 meters per second, and to relative to Sun or something like that. Whether two events are simultaneous depends on the frame of reference. Two lightning in a strike, the railroad car and ground at each. Speed of light is constant. Okay, so what? Einstein supposed or pondered, what would be the consequences of a constant speed of light? Independent of a state of motion, if at constant velocity, any observer traveling at constant velocity will see light behave normally and always at the same speed. It means when we are here, we really think everything is ordinary and normal and usual. Mathematical consequences are very clear, forced to give up Newtonian view of space and time as completely separate concepts. It was in the time of Newton and Galileo that both of them, they were separate concepts. But now, there is no such a thing. There is space-time. There is no space and time. Both of them are one concept. Providers rules to compute observable comparison between observers with relative velocity. Then, relativity means relative state of motion. Remember, everything is moving. One person's space is another time. This space is for us, but somebody else in the other galaxy could see something else. I will tell you next. If simultaneity is broken, that we noticed by the special relativity, simultaneity was broken by special relativity. If simultaneity is broken, no one can agree on a universal time that suits all. The time for me is something, the time at the same time for somebody in galaxy Andromeda would be something else. The relative state of motion is very, very important because the speed of light is constant and finite. For all observers, space and time are unavoidably mixed. We have seen an aspect of this in that looking into the distance is the same as looking back in time. Imagine a spaceship flying by with a strobe flashing once per second as timed by the occupant. The occupant sees the strobe as stationary. I'm stationary here, stationary here. You see flashes in different positions and disagree on the timing. Between flashes, space and time are mixed. See description of light clock in text. Space and time mixing promotes unified view of space-time. Then one person, the space is another time. It means there is just one concept in the name of space-time. There is no two separate things, one space, one time. Events are described by 3 spatial coordinates plus the time. Then, if we are going to describe here, we are not allowed on the basis of special relativity that say, okay, this is our length, and this is our width, and this is our height. There is something else, time, the fourth. Then time dilation, moving clocks, tick, slow. Length contraction, moving rulers or any kind of objects, appear contracted. This is length contraction. I couldn't delete the sentence over there. Length contraction. So moving observers see that objects contract along the direction of motion. Length contraction, again, also called Lorentz contraction, Fitzgerald contraction, because the equations was proved by Lorentz. Note that there is no contraction of length that are perpendicular to the direction of motion. Recall Michelson-Morley the experiment. Results consistent with one contracting. What is the meaning of life now? The answer 42 is wrong. The correct answer is 45. There was a man in the name of Douglas Adams that he wrote the books Hitchhikers to the Galaxy. Hitchhike means the people that they do this and they go free for something. He said they hitchhiked to go to Galaxy free, but that novel, a part of that, a computer is talking to the guy, and the guy asked the computer, well, what is the sum of 6 multiple 9? Of course, the answer is 54, yeah? But the computer answered, it is 42. And the guy suddenly said, why? He said, because the universe, everything in life is somehow complicated, sophisticated, and is not good for the human being. Douglas Adams wrote The Hitchhiker's Guide to the Galaxy. He added a central joke. That was a joke for, really, Douglas Adams, but which has become more famous. That joke that I told you, it was a central joke, which has become more famous over the years than the novel itself. The answer to the ultimate question of life, the universe, and everything is 42. I checked Google and you Google it. More than hundreds, thousands of articles, papers, that really the life meaning is 42. And they brought a lot of scientific and especially mathematical evidence about the meaning of life is 42. Okay? Now I'm telling you no. That, however, it was a joke, that was wrong. The meaning of life is 45. But I will prove that here. The meaning of 45 degrees. The light cone represents the idea that the direction of the light flash doesn't depend on the motion of the source, but just on the event at which the light flash is emitted, propagated, emitted. In addition, by the Einstein principle of relativity, all observers, regardless of their motions, must, because of the Maxwell's laws, measure the speed of light to be the same constant in all directions. That is to say, all observers will universally agree on the light cones at each event. That means that each observer drawing a space-time diagram, which he is at rest, must have the word lines be back. What is word lines? Word lines of light flashes at the same angle of 45 degrees from his word line. His time axis is the word line. Everybody, as a stationary or observer, has a word line, time axis, and 40 degrees from his plane of simultaneity, his space axis. Here it is. Stationary body, vertical track. We are doing this now. This is our time and this is our space. When we are moving, this is our track. Slow moving body, for example, when you are going to Amsterdam with a velocity, for example, speed of 150 kilometers, a little bit like that. And when we go to a spaceship or something like that. But for the speed of light, this is the only way to go through to the space. For the speed of light, the only way to go through, and everybody can see that, is 45 degrees. This is the meaning of life, you will see that. Time like creep. This is the velocity that, but not very close to speed of light. this is 45 degrees, and space-like trip is among that. Geodesic, shortest path between 2 points. Particles follow geodesic in space-time. You remember when we were in high school or primary school, always they ask you, what is the shortest way? And always, what was the answer? The shortest way between 2 points? Exactly. It is 100% wrong. Now we see that. The axes are usually chosen so that light travels at axis. This is the coordinates, 3 dimension. But we should plus the 4th dimension here. This is the cones of time. Many problems in the special relativity can be analyzed in terms of space-time diagrams. That is the problem. Word lines, I told you many times, because of this, massless particles travel along null word lines. What is massless particles? Can you tell me one kind of example?
Neutron.
Please?
Neutron.
Neutron, that's it. Okay, very good. Photon, the light. Okay, that was good. Electron, massive particle. Who is massive particles? One example. You are massive. This is massive. Massive particles travel along time-like word lines. Note that their path always lies within their past and future light. We back to massless particles again. But what is the degree of this? What do you think?
45.
That's it, 45 degrees for the light, and also this is the word line also. Time dilation is coming out of that. This effect called time dilation. Clock always ticks most rapidly when measured by observer in its own rest frame. We are observer, and this is our rest frame. Clock slows, ticks take longer from perspective of other observers. When clock is moving at v velocity with respect to an observer, ticks are longer by a factor of Lorentz. This is the Lorentz factor. Gamma, it is wrong, it's not equal, it's congruent. You know what the congruent is, yeah? It's congruent to 1 over a square root of 1 minus v squared over c squared. We're back to this. It's very important for our discussion, how we really calculate the time dilation.
Sorry, could you explain in these 2 last slides, exactly you explain it now, that while we go faster, the time goes slower.
Yeah.
You want to explain this, and how do you relate it with that 45 angle? And I want to understand it somehow more, because always I hear about it.
Yeah. Are you asking me about what is that 45 or what
the
is
relation between this angle?
Yeah, there is no relation. The only thing is, this is a fact that they notice that all the lights are going to that 45 degrees. But if you let me to go to some next slide, you see what is exactly the other side of that 45 degrees. A part of that never seen by you, by me, by any kind of observer. Then the only way that you can see everything in the space is from the word line and that 45 degrees, because the light is going through that 45 degrees. The other part of the space and the universe is dark for us forever, and we never can go see what is happening over there. But somehow we have some other instruments that can weight the whole universe, can see a lot of things from the other galaxies by the gamma radiation or something. But if you just look at not this, 2 or 3 next slide, we'll back to that. The Lorentz transformation, there is a prescription, not a medical prescription, but really he prescribed that. for transforming between observers in relative motion. Prime coordinates belong to observer moving speed velocity along the x direction relative to unprimed. Note, mixing of x and t into x prime and t prime. Time and space being mixed up. I'm not going to ask you really understand the mathematical formulation, but if you put the numbers on it, it works. I will show you. And this gamma is very important. That gamma factor is the function of velocity. Here, put the numbers. For now, when the velocity is 0, the gamma is 1. Then we really don't notice what is time dilation because of this. And again, if you put something like 6 part of speed of light, it is, again, not so far from that, but it's 1.25. But the most important one is when you are closing to the speed of light, everything would be changed. Everything would be changed according to gamma factor of Lorentz. About 8, it is 1.67. And if you put it, the velocity is exactly very, very, very close to C, the gamma is finite. What does it mean? It means the length contraction, for example, all the universe is going to speed of light, the whole universe could be something like an electron, the length contraction. And the time would be nothing. The time would be nothing. What does it mean? It means they don't notice any time. They don't notice any time. The light is not going to see what is happening in the name of time. Light is going everywhere without time. Light is going everywhere without noticing the time, because they are going through the 45 degrees. But for us, why we cannot do such a thing? Because we are massive, because we are not massless particles, because we have body. Okay? Why does gamma do? What does gamma do? Time dilation clocks on a moving platform appear to tick slower by the factor gamma. And that 6 that I showed you, 1.25. So moving clock seems to tick off 40 seconds per minute. Then, for this velocity, there is no 60 seconds per minute. It is just 40 seconds. Then the clock really ticks slower. And standing on platform, you see the clocks on a fast-moving train tick slowly. People age more slowly, though to them all is normal. Although for them everything is normal. If we go, for example, even to the speed of light, we don't see anything abnormal or something unusual. Everything is normal for us. Length contraction. Moving objects appear to be compressed along the direction of travel by the factor gamma. Again, the same for that. Standing on a platform, you see a shorter train slip past. Through the occupants see their train as normal length. Special relativity reveals that C is not just the velocity of a certain phenomenon. Speed of light is not just the velocity of a certain phenomenon. That phenomenon is light, namely the propagation, emitting of electromagnetic radiation, light, but rather, this is the whole story. Rather, a fundamental feature of the way space and time are unified as a space-time. One of the consequences of the theory is that it is impossible for any particle that has rest mass to be accelerated with the speed of light. Give me an example for rest mass. What?
Rest mass for photon.
For what? Neutron? No. Now rest mass is us. Rest mass is this. Okay? Massless is those particles. But rest mass means things that they have mass, the real mass that it was exactly working in Newtonian transformations. Yeah? But for now, why don't we see relativity every day? Why in our daily life? Why you don't see that? Because we are so slow relative to see. Really so slow. Yeah? That length, contraction, and time dilation don't amount to much. For example, in a freeway, you are going, I said 30 meters, but it could be, you can say 100 kilometers per hour. But it is nothing. It's 10 minus 7. And then it is nothing. Gamma is 1. Beep, 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 1. Exactly, it is 1. When gamma is 1, or very close to 1, you cannot notice any time dilation or any length contraction. And even for Earth is orbiting around the sun, but it is, again, the gamma is very, very small. It's 10 minus 4. Then we don't notice. But precise measurements see this clearly. There are many evidence and many facts nowadays from 30, 35 years ago till now. There are many evidence about that. Then what is the usefulness of relativity of Einstein in our daily life? Okay, we cannot go anywhere without Einstein. How? Because of GPS. Global positioning system is working properly on the basis of relativity. It means without relativity, GPS was a toy. Then at least we have one thing good from special relativity. To know what good is fundamental physics to the person on the street, see the next slide. Well, what is goodness of special relativity for the ordinary people like us, you? This is how Einstein proved we are wrong, and Einstein last words to Iranian students at Delft University. Cheers. That's it.